Hi, my name is Shafat Islam, and my ZID is Z5482112, and my experiment will be Experiment 1, Understanding the Solar System. In this experiment, I explore how celestial bodies interact under gravity by observing their orbital behavior using a simulation. Let's start by reviewing Kepler's laws. The first law, or the law of ellipses, states that planets orbit the Sun along elliptical paths with the Sun at one focus. What this means is that a planet's distance from the central body, which in the Earth's case being the Sun, is constantly changing throughout its entire orbit. Kepler's second law states that a line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. So as the planet moves closer to the Sun, its radius vector shortens, and to conserve angular momentum, its tangential velocity must increase, and vice versa when it moves away. Kepler's third law reveals a precise mathematical relationship, suggesting that the square of a planet's orbital period must be proportional to the cube of the semi-major axis of its orbit. Newton's synthesis in the 17th century not only explain why Kepler's laws work using force and motion, but also generalize them to all gravitationally bound systems, suggesting that the mass of a central body has to play a part in the orbital period of its orbiting body. Hence, Newton's universal law of gravitation comes into play to give us the magnitude of proportionality between these two factors being 4 pi squared over gm. In a two-body system, both objects orbit a shared center of mass, otherwise known as a barycenter. Earth and the Moon, for example, orbit around a point of about 4,700 kilometers from Earth's center. This offset makes Earth wobble slightly. If we fasten the speed of the simulation, we could see that, and we can also see that the planet traces a small loop around the barycenter, while the Moon traces a larger loop. This mutual motion reflects Newton's third law, as the gravitational force the Moon exerts on the planet is equal and opposite to the force the planet exerts on the Moon, so both bodies accelerate toward their common center of mass. Across question 1, question 4, and question 7, the center of mass always lies within the star due to its dominant mass. In question 1 and question 4, despite the planet's mass increasing by a factor of 1.5 in question 4, the barycenter still remains only slightly offset, and the orbital shape and the period stay nearly unchanged. In question 7, increasing the star's mass by a factor of 1.5 and lowering the planet's tangential speed caused the planet to spiral inward due to a stronger gravitational pull. As the radius shrinks, the force vector lengthens, and this reflects an increase in attraction between the Sun and the Earth. So the Sun shifts slightly, but its much larger mass results in minimal acceleration. Now, in the planet, Moon versus star-planet systems, the key difference lies in their mass ratios and distances. In a Sun-Earth pair, the star's immense mass places the barycenter deep within the Sun, making it appear stationary while the planet orbits. If the masses were closer, the barycenter could even lie outside both bodies. So greater separation would also shift the barycenter further from the larger object. Now, let's explore how to calibrate the distances using the simulation's measuring tape. One grid line corresponds to 73,045,340 kilometers, which is roughly about 0.5, a half a astronomical unit. So this meant that two grid lines equaled roughly 1 astronomical unit, within 2% off from the official value of 149,597,870 kilometers. Now, using these distances, I tested Kepler's third law in 4 circular orbits at 0.5, 1, 1.5, and 2 AU. At each, I adjusted the tangential velocity in order to get circular orbits. We can see that the orbital period stretches from 132 days up to 1,012 days. So to check this relationship, I had to compute the Newtonized formula for each orbit and compare it to Earth's ideal value of 133,225, as according to the third law, this should be the constant at any orbital distance around the same central mass. Despite minor measurement errors and idealized assumptions, the resulting ratios cluster within roughly 5% over and under the Earth's constant. In simple terms, the farther a planet is from the Sun, the longer it takes to go around once and the slower it moves. This is a direct consequence of Kepler's third law, and the orbital velocity equation v equals to the square root of gm over r. For example, Mercury, at just 0.39 AU from the Sun, zips along its orbit at about 47.9 kilometers per second, and completes a year in only 88 days. By contrast, Neptune lies more than 30 AU away and crawls around the Sun at only 5.4 kilometers per second, taking about 165 Earth years to finish a single orbit. So Mercury, being the closest to the Sun, is thereby the fastest planet, and Neptune, being the farthest, had the slowest orbital speed and the longest year. So what did this experiment teach me? This experiment visually reinforced how Kepler's laws, gravity, and barycenters govern orbital motion, and showed me that stable orbits rely on the balance between tangential velocity and gravitational pull, and not just mass alone. Thank you for joining this journey through the solar system with me. Keep exploring the stars.